Good morning, everyone. A very good morning. Shall we begin the session? Today's topic is relocation. That is a part of topic number 7. In the last class, we have discussed about the compilers, drivers. Okay. So relocation is a process by which we can use symbol resolution step that has a symbol reference in the code with exactly one symbol resolution, symbol definition, symbol data entry point in one of the input object module. And at this point, the linker knows the exact sizes of the code and the data section in its object module. And it is now ready to begin the relocation step where it merges the input module and assigns a runtime address to each symbol. So that assigns runtime address to each symbol, whatever symbol that is categories, whatever symbol that is available in this category. And relocation consists of two steps. One is the relocation section and the symbol definition. In this step, the linker merges all the sections of the same type into a aggregate section of the same type. For example, when you talk about the data section from the input module that are merged into one section, that will become the total data section that is used for the memory address to the new aggregate section to each section that is defined by the input module, and for each symbol that is defined in this one that is used for the ready module that is used for the input module. And when this step is complete, every instruction and the global variable, whatever the instruction, whatever the global variable that is used, so that global variable in the program has a unique runtime entity, runtime memory address. The next is relocating the symbol references, whatever the symbol reference that is available within the section. So in this step, the linker modifies every module reference in the bodies of the code and data section so that they point to the correct runtime addresses, and whenever it is performing this task, so linker relies on the data structure in the relocatable object modules known as the relocation entries that is described over the next. The next is relocation entries. So when an assembler generates an object module, it does not know where the code and data will ultimately be stored in the memory. Nor does it know the location of any externally defined function or global variable that are referenced by the module. So whenever the assembler encounters a reference to an object whose ultimate aim or location is unknown, it generates a relocation entry that tells the linker how to modify the reference when it is merging with the object file into the executable file, object file, whatever the executable that we are using in this one. So relocation entries for the code are placed in .rel.text, and that entries for the initialized data are placed in a .rel.data. So entries are available in this one and the addresses are available in the rel.text. And this figure shows the format of an ELF relocation entry, and the offset is a section offset of the reference that needs to be modified, and symbol identifies the symbol that will be used that the modified reference should point to, and the type tells the compiler or the linker how to modify the new reference. So this defines 11 different relocation types, some quite arcane. We are concerned with the two most basic relocation types. One is the R386 PC32 that will relocate a reference that uses a 32-bit PC relative address. And recall from section this one, a PC relative address is an offset from the current runtime value of the program counter, that is PC, and whenever the CPU executes with the PC relative addressing, that forms an effective address by adding the 32-bit value in the instruction to the current runtime value of the PC. And it is also used to relocate a reference that uses a 32-bit absolute address. So one is a 32-bit PC relative address, one is a 32-bit absolute address. And with this absolute addressing, the CPU directly uses a 32-bit value that is encoded in the instruction as an effective address without the further modifications. Without modification, without PC, that is the program counter that is used for the PC relative addressing, that also forms an effective addressing address. The next is relocating the symbol references. Then that shows a pseudocode for the relocation or the linkers relocation algorithms. and this will iterate over the sections and sections, and the entry will be done for each section. And for the concreteness, assume that each section S is an array of the bytes and each correlation entry R is a struct of the type with relevance as defined over here, and also assume when the algorithm runs, the linker has already chosen runtime addresses for each section that is denoted by the address, that is denoted by the symbol, that is denoted by the R dot symbol, that uses the 3 byte array or the 4 byte array. This is a for each case, or the for each loop is available for each section S, for each relocation entry R. Then yes, reference BTR equals to S plus R dot offset. Then relocate to the PC relative reference. If R dot type is equal to, that is compared with the R386 PC32, then address S plus R dot offset. Then reference BTR equals to unsigned address R dot symbol plus pointer ref ptr minus ref address. Then r dot type equals to r38632. Then reference ptr equals to unsigned address r dot symbol plus reference ptr, that is used for the relocatable reference. The next is relocating the PC relative reference, that is used with the swap, that is used with the relocation array. Or the 32-bit reference array, that is used with the 4 decimal, that is stored with the little endian byte order. And so the address r dot symbol equals to address swap, that means symbol is swapped with the these 080483C8. Then reference address is address plus r dot offset, and that is used with 0 and 7. And then update the reference from its current value to 09 so that it will point to the swap routine at the runtime. Then reference BTR, unsigned address r dot symbol, reference BTR, reference address. And at the runtime, the call instruction will be stored at register register, and the CPU executes a call instruction. The PC has a value this. This is the reference, that is the address of the instruction immediately following the call instruction. And to execute the instruction, CPU performs the following steps. Push the PC into the stack. PC is PC plus 0 into none, that is the reference given over here. Then the next instruction is to be executed is the first instruction of the swap routine, which of course is what we want. That is used by the call reference with an initial value of -4. And next is relocating absolute reference. So one is the relative, that means that it changes when we move from one location to another. The absolute reference that do not change, that remains a constant whenever we move, whenever we swap from one location to another location. This is the end pointer buffer P0 buff 0, then the location array or entry, unsigned integer, address r dot symbol, reference PTR. And in the executable object file, the reference has a following relocated form. This is the form. This is 54940408. And in other words, the linker has decided that at runtime that the variable buff P0 will be located at the memory address, and that will be initialized to this address, that is 0 into 804945. This is the main, this is 5589E5EC08, then swap. Then EAX, EAX, EVP, ESP. Then next is the relocated data section. Next is executable object file that we have already done, that whenever we are using the exe file or the obj file, that is executable object file, that have a segment header file, that have a table, that have a defined function, that have a init section. That is used with the program initialization code, that is a fully linked relocatable code that needs number or the no REL section. Yes, this is used with the segment header table. This is the map contiguous file. This is the ELF header. segment header table, init, text, show data, data, BSS, symbol table, debug, line, str tab, or the section header tab. The symbol table in debugging info are not loaded into the memory. Read write memory segment, read only memory segment. So the read only memory segment till RO data, then read write till BSS, then symbol table and debugging that is used with the str tab or describes object. Then the next is loading executable objects file. That is how to load this one with the use of Unix shell command line. That is executable object file from the disk into the memory that runs the memory by jumping to the first instruction of the entry point, and the process of copying the memory or the program into memory and then running it is known as a loading. And the runtime heap follows on the first 4 KB line address pass the read-write segment that grows up with the calloc or the malloc library. The next is kernel memory, user stack, memory map, shared library, runtime heap, read-write segment. This is loaded. Yes, whenever the loader runs, it creates a memory image by using the header table, by using the startup code, by using the startup. This is a pseudocode for the startup. Now the last part is dynamic linking with the shared libraries. Yes. How to how to use the dynamic linking, that is the runtime linking with the shared libraries if there are any shared library that is available to the application program or the static program. That will have significant disadvantages. Static library, like all software, that needs to be mentioned and updated periodically. And if the application programmer wants to use the most recent version of the library, they must have somehow becomes aware about how the libraries are changed or how the predefined methods are changed and then explicitly relink their program against the updated library. Now there are two concepts. One is the shared library that are the modern innovation that the address or that address the disadvantage of the static library. And shared library is an object module that at runtime can be loaded into the arbitrary memory address and linked with the program in the memory. And this process is known as the dynamic linking that is performed by a program known as a dynamic link. And shared library can also refer to as a shared object that form the Unix system that is typically denoted by the S or suffix that is used with the DLL dynamic link libraries. And that is shared in two different ways. First, in any given system, there is exactly so file for a particular library. And the code and the data in this so file are shared by all executable object files that are referenced in the library. Now this summarizes the dynamic linking. This is the one of the method how to use the dynamic linking over here. This is translator, this is linker, then loader, then dynamic linkers. Then how to load and link the shared libraries from the application. To use a shared library from the applications also, that is also possible by using the distributing the software, by building the high performance web server that uses the dynamic content such as a personalized web pages. The main idea is to generate dynamic content in a shared library. That is one of the main things, because we are using the DL open function that links the shared library address also. Yes, this library is used in the or used with the file name that are resolved using the library that is resolved that is open with the RTLD global flag. And if the current executable was compiled with the R dynamic flag, then in the global symbol are also available for the symbol resolution. And the flag monument or the flag argument that is available in either RTLD now, which tells a linker to perform or to resolve references to the external symbol immediately, or on the RTLD lazy flag that instructs the linker to defer the symbol resolution until the code is available from the library or until it is executed. This is include DLF, cn.h, DLF, cn.h. Now these are the various functions that also show the libraries null functions that is getting the pointer to the advec function that is loaded up. Then load the dynamic shared library that contains advec. Then unload the shared libraries. The next is PIC, position independent code. Yes. Now at last there is a summary of this, that is the dynamic linking or linking is done at the compile time, linker load time. Yes, and the static linkers are also available at the compile time, drivers, the GCC. So the next chapter is chapter number, I think, 8. Yes. This is control flow. So this chapter we will take in the next class, that is in the tomorrow's class.